Welcome to a video on space curves represented by the intersection of surfaces. The goal of this video is to determine the intersection of two surfaces and then express the intersection as a vector-valued function. Let's take a look at our first example. Here we want to graph the two surfaces and then determine the equation of the intersection using a vector-valued function. Let's start by taking a look at the graph of these two surfaces. We can see we have a paraboloid and a plane. Let's angle this so we can get a good idea of what the intersection looks like. We can see here that the intersection is a circle, but it's shifted up 1 unit on the z-axis. So let's go back and figure out how we can determine what the equation of this circle would be. What we're going to do is find a solution to this system using a set of parametric equations, and then once we have the parametric equations, we're going to rewrite it as a vector-valued function. So since the intersection is a space curve, in parametric form we're going to have an equation for x of t, y of t, and z of t. We want these three equations to satisfy both of these equations. Well, right away we know that z has to equal 1 based upon this second equation. So now we know that z of t must be 1, and we can use this to perform substitution into the first equation. So replacing z with 1, we would have 1 equals x squared plus y squared. So now we need to determine what we could use for x and y in terms of t to satisfy this equation. Well, whenever we see something like this should remind us of the trig identity sine squared theta plus cosine squared theta is equal to 1. So using that identity, we could let x equal cosine t and y equal sine t. And if we perform substitution here, we'd have cosine squared t plus sine squared t, and this does equal 1. So both of these equations are satisfied with these three parametric equations. So the intersection of these two surfaces expressed as a vector-valued function, in component form, the x component would be cosine t, the y component would be sine t, and the z component would be 1. Of course, we could also express these as a sum of the unit vectors I, j, and k, but I'm going to go ahead and leave it in component form. Let's go and take a look at another example. Again, we want to graph the two surfaces and then determine the equation of the intersection using a vector-valued function. We have x squared plus z squared equals 4 and y equals z squared. Here's the graph of the two surfaces. If we rotate this around, we can see the intersection of these two surfaces is outlined here in green. And our job is to determine the equation of the vector-valued function that represents this intersection. So let's go back and do it. Because it's a space curve, if we can define x of t, y of t, and z of t that satisfy both of these equations at the same time, we can then rewrite these equations as a vector-valued function. So looking at this first equation, we have x squared plus z squared is equal to 4. Well, if this was equal to 1, we could let x equal cosine t and z equal sine t. But it's not, it's equal to 4. So in this case, if we let x equal 2 cosine t and z equal 2 sine t, this would satisfy the first equation, because if we square 2 cosine t, we would have 4 cosine squared t. And if we square 2 sine t, we'll have 4 sine squared t equals 4. If we factor out the 4, we have the identity that we want, cosine squared t plus sine squared t, which is equal to 1 and satisfies that first equation. So now we're left with satisfying the second equation, given that y is equal to z squared. Well, if we defined z as 2 sine t, we can just square z to get y. So we can define y as 4 sine squared t. which means the intersection of those two surfaces as a vector valued function would have an x component of 2 cosine t, a y component of 4 sine squared t, and a z component of 2 sine t. Now I should make a note that these parametric equations could be defined in a different way, meaning we could have let x of t equal 2 sine t and z of t equal 2 cosine t, which would have changed y of t. So the way of expressing this vector valued function is not unique, but it does satisfy these two equations, and therefore it does represent the intersection of those two surfaces. Here we have x squared over 9 plus y squared over 16 plus z squared equals 1 and y equals x squared. And we only want to consider this when z is greater than or equal to 0. So notice that I'm only including the graph above the xy plane, and again we can see the intersection would be this curve here. And again, our job is to determine what that equation would be as a vector valued function. So we'll first express the solution as a set of parametric equations, so we'll need x of t, y of t, and z of t. Now this does not remind us of any trig identity that we're aware of, so this one is going to take a little bit more work. Let's take a look at the second equation first. If we have y equals x squared, if we let x equal t, that would make y t squared. So these two equations satisfy the second equation. Now we're left trying to satisfy this first equation in terms of x, y, and z. But now that we've already defined x and y, let's go ahead and perform substitution in for x and y. So x squared would be the same as t squared. So we'd have t squared over 9 plus y squared would be t squared squared, or t to the 4th, over 16 plus z squared is equal to 1. Now we are looking for a way to express z as a function of t. Notice this equation now only has t's and z's. So if we solve this equation for z, it would be a function of t. So let's go ahead and do that. We're going to go ahead and subtract these two terms to the right side. So we'd have z squared equals 1 minus t squared over 9 minus t to the 4th over 16. And now we can take the square root of both sides. And because we're only considering z greater than or equal to 0, we're going to use the principal square root here. We're going to have z equals the square root of 1 minus t to the 2nd over 9 minus t to the 4th over 16. And I'm going to go ahead and leave it like this. So now we can express z as a function of t. Which means we can now express the intersection of these two surfaces as a vector valued function, where the x component is t, the y component is t squared, and the z component is the square root of 1 minus t to the 2nd over 9 minus t to the 4th over 16. Okay, that's going to do it for this video. I hope you found it helpful.